Welcome to Physics 2220. This is our second semester, 2220. Second semester of the Physics for Scientists and Engineers. We're starting this particular semester with the chapter covering oscillations. So an oscillation, you may very well be familiar with the term. An oscillation is any sort of system that repetitively goes through the same motion over and over and over again. A common example, let me jump over here. I have a couple things ready. So this is a program called PhET, it's Physics Education and Teaching, and they have simulations. You may be doing some assignments using simulations this semester. If I put a mass, I drag it up here, and I hang it on a spring, then the system, this mass spring system, will oscillate. Now, right now, I have some damping, meaning there are forces that are causing some of the mechanical energy, the potential and kinetic energy, to turn into thermal energy, which we can see that over here on the left side. So the graph, these energy graphs on the left side, it's representing this thermal energy. Now we have this mass at equilibrium at the moment. I'm going to check the box up that's on the right to show me the line that represents the mass equilibrium. We know the spring, if I click the box up top, the natural length, meaning before the mass was attached, that's where the spring was located. Now that we've attached the mass, we have the gravitational force of the mass pulling down, and then the mass is being pulled upwards by the spring as well. Now, as far as where we're going to start with oscillations is I just deleted the thermal energy on the left side. I turned down the damping to none on the right side because we're going to talk an ideal situation first. Meaning we're going to assume there's absolutely no forces, nothing happening to transform our energy to other forms of energy, the thermal energy. So the system has a certain total energy right now because of where the simulation is calling height of 0, which is at the very bottom. They're showing us a height of 0 meters. And so gravitational potential energy is relatively large because this mass is located at a distance above this height of 0. There is energy, potential energy in the spring because of it has been stretched. Now, if I take this mass and I pull it downwards, that total energy has increased because I've caused the spring to stretch more. The gravitational potential energies decreased because the mass is closer to that bottom line where height is equal to 0. But the elastic energy is bigger because that stretch is squared, which I'll remind you of these equations when we get back to the whiteboard. But, oops, I didn't mean to pull it off. Let's do this again. So if the mass comes to rest, so let me get it to rest again. So going back to no damping, get rid of the thermal energy that was generated because of the pull. If I pull this mass downwards and let go, we now see this system oscillating up and down. And again, because I turned off the damping, the simulation is assuming no energy is being turned into thermal energy. And so we would watch this continue forever and ever and ever if we were to sit and watch it. Now I'm going to put it on slow for just a second so that we can look at the energy graph on the left. That total energy bar is never changing. It's constant. And that is unique to this situation where we're assuming ideal oscillations. What's happening is the energy is changing between the two types of potential energy, gravitational and elastic, as well as kinetic energy when the mass is moving. But the mass will oscillate up and down indefinitely because of this assumption that there is no damping. So a mass spring system is an example of an oscillating system. Now, of course, realistically, there is damping. The mass spring system would die down, its motion would die down as time goes on, and it would eventually come to rest. Because in a realistic situation, we cannot get rid of all sorts of damping. Another situation that's common is a pendulum. So this simulation represents two simple pendulums, penduli. So by simple, all that mass is concentrated at the end of a string of some sort. Here I pulled them to two different angles and got them swinging back and forth. Both of these represent an oscillating system, meaning they're repetitively going through the same motion over and over and over again. This particular system is representing an ideal system as well, because if you look at this bottom right-hand corner over here, friction is turned down to none. Okay, so we're going to come back and we're going to start first. We're going to talk about ideal oscillations and how to represent the motion both graphically and in terms of equations. When we're talking about ideal oscillations, we mean there's no thermal energy created. We mean that the mechanical energy, meaning the potential energy, and the kinetic energy, if we add those up, this total energy is constant. So any change in potential energy is going into a change in kinetic energy. Ideal oscillations, we call this simple harmonic motion. That's a common phraseology you will see relating to ideal oscillations. Now, if we were to graph the motion, for example, that one situation where we had the mass in the simulation, I had pulled it downwards and then released it. We could graph the motion, this Y motion up and down. So the mass started oscillating up and down. We could graph that versus time. Since I pulled the mass downwards and released, I would start my position graph at the lowest possible value where I pulled the mass down to, and then it oscillated up to a maximum height. This is where I pulled it to. Initially, well, it doesn't say initially. Let me try that again. Initially. So this is my Y naught value. Now I'm using Y simply because the mass was oscillating vertically up and down. So this vertical axis is representing the position of the mass. The horizontal axis is our time, at what moment in time that we are seeing it or looking at it. So where the mass is at any moment in time. Any simple harmonic motion, any basic ideal oscillator, will have a position versus time graph that is sinusoidal. Now, this one that I've just drawn is technically a negative cosine graph because it starts at a negative maximum value and then oscillates up and down from there. Now, a couple of things to recognize and learn. That mass, as it oscillated up and down, this maximum distance downwards was the same as how high it went upwards. Above this y equals 0 line represents the equilibrium line, where the mass on the spring was at rest. And so once I pulled the mass downwards and let it oscillate, this y naught, this initial pull downwards, is equal to y up here, the maximum height above equilibrium. The mass then oscillated and fell down to this same initial y naught, that same initial distance from equilibrium, and then as it was springing back upwards, it went to the same maximum height again. And we call this maximum distance from the equilibrium position the amplitude. So amplitude is the maximum distance the oscillator, whatever it is that is oscillating, it's the maximum distance it travels from equilibrium. In SI units, that would be in meters. We could certainly write it in centimeters, millimeters, that type of thing, depending upon how big those distances are. All right, so amplitude is something that is going to be characteristically describing these oscillations. Another term for us to recognize is if we look at this initial moment in time when the mass is at its lowest position, we know it travels all the way up and then all the way back down such that it gets back to that maximum distance where I pulled it down to initially. If we measure between the first time it's at that lowest point to the next time it's at its lowest point, we call this the period of the motion, and we use a capital T. You might remember that we used capital T last semester in terms of the period of orbit, so like the Earth orbiting the sun. Capital T was the amount of time it took the Earth to orbit. Capital T, still same general idea, in that the amount of time it takes to complete one full cycle of motion. And we're going to relate this to circular motion in just a minute. So we'll see how T applies there as well. Period, we can essentially just think this is the number of seconds required, or, well, let me not put required, number of seconds to complete one oscillation. What that means is it's the amount of time for the mass to oscillate from one position, to the exact same position. And we mean also moving in the same direction. So period, every single oscillating system is going to have its own unique period. And we'll talk about what determines that period in terms of a mass spring system versus that pendulum. So just to represent this really quick, let me draw another graph. Same graph, just clean. So time, position, this was a negative cosine graph. When we talk about the period, I represented that just before as the lowest point, the time to get to the lowest point again, which is totally valid. But that's not the only way. I could, if I wanted to talk about this point right here, this position represents when the mass is moving upwards through the equilibrium point, where it would have been at rest if it wasn't moving at all. If I want to talk about period, technically the point right here, the mass is moving through equilibrium. But it's not moving upwards, it's moving down. So it's moving down through equilibrium. So the distance from here to here is not t. So even though it's the same position, because the mass is moving in a different direction is what makes this not the period. The period, I would have to measure all the way over to here, where the mass again is moving through equilibrium and upwards. So the period would be right here. And so period is the amount of time to complete or go through one full oscillation. And we can identify any points. We could do the top to the top, that's fine. Any two identical points on the graph will represent the period. Another term you're going to see and work with is frequency. We use a lowercase f for frequency. It is simply 1 over the period. So if period is the amount of time, how long it takes for a oscillator to go through one oscillation, then frequency is the inverse of that. It's the number of oscillations, how many times it oscillates in 1 second, which it can be a fraction. It doesn't have to be a whole number. So number of oscillations per second, you can think of period as the number of seconds for one oscillation. And so that's how we get frequency and period being inverse of each other. It's really easy to confuse these two. So be very careful in describing the units. The units themselves will show you which one you have. It's not hard per se to go ahead and calculate this, but we will actually, it's common to see them inversed. For example, reading a number of seconds from the graph and calling that frequency instead of period. So just be careful in terms of those. One other term that we're going to see is called angular frequency. We use omega, the Greek letter omega, to represent this. We used omega to represent an angular speed in last semester when we talked about circular motion. You might recall that to convert between, say, a revolution and a radian was the factor of 2 pi, because we know there's 2 pi radians in a revolution. So the way we represent this in terms of oscillations, if you imagine we have our mass on our spring, it's going to be oscillating up and down. Imagine a disc that has a peg on it. So this peg sticks out farther. So if you've ever done one of those discs where you spin to see if you win something, there's oftentimes, well, there has to be pegs sticking out so that the little arrow will stop it from spinning and you can see what you won. So this disc has one peg on it. And this disc is going to oscillate, or it's going to rotate at an angular frequency of omega, where omega is in radians per second, where omega is essentially 2 pi times the frequency, where the frequency represents the frequency of this mass spring system. So I've drawn the peg at the bottom to represent this simulation system we looked at, where I pulled the mass down and released it from rest, and it oscillated upwards. So if we imagine, let's see, how well I want to draw this. Let's imagine a screen right here and some sort of light source over here shining on this disc with the peg. At this specific moment in time, when the peg is at the very bottom, we would see a shadow on the screen at this lowest point. So essentially, the shadow of the peg right here. And of course, it doesn't stick out from the screen. I'm just drawing it in a way that I can. As this disc rotates, so not much long later, the peg's going to be right here because the disc has rotated. That means the light source will cast a shadow right here instead of this lowest point. If we were to continue looking at this disc rotating, the peg would be here at a moment in time, which means the shadow would be right here. And then the peg would be here. So this disc is rotating counterclockwise. Here's the peg. There's the shadow. So we would see this shadow essentially start at this lowest point, and then it would oscillate up and down and up and down. The shadow position, if we were to graph the shadow position as a function of time, so just where on the screen, up and down, y = 0 would be that middle point, down here would be that initial y naught. The position of this shadow is going to go up and down and up and down, just like the mass on the spring is going to go up and down and up and down. And so we can model oscillations as kind of a one-dimensional circular motion. How fast this disc would have to oscillate up and down, to oscillate and rotate counterclockwise to match the up and down motion of the mass on the spring. This is where omega comes from and is called an angular frequency. Is from this relationship between this circular motion that spinning of the disk with the peg and its shadow versus, and comparing that to our oscillatory motion. And that's why we can go ahead and say angular frequency, omega, and relate that to oscillations. Now, if you remember, or not, I suppose, units of omega will always be radians per second. And that's why we have this factor of 2 pi here, is since frequency is oscillations per second, we have to multiply by 2 pi to get to radians per second. So one single oscillation of the mass up and down on the spring is equivalent to one full revolution of this disk, and then the motion of the shadow that we would see on the screen. So we can say there's 2 pi radians for one oscillation, because when we equate that to the circular motion, one oscillation equates to one revolution. All right, so our basic terms for any ideal system. So simple harmonic motion, we have period, meaning the amount of time it takes to complete one oscillation. We have frequency, meaning the number of oscillations per second. We have angular frequency, so just in terms of radians per second instead of oscillations per second. These 3 general terms are related. Frequency is 1 over period. Omega is 2 pi f, which means if I put 1 over period in place of f here, I could say omega is 2 pi over t. These general terms can be used to represent any type of ideal oscillation. Because an ideal oscillation is going to be a sine or cosine graph, we can write generic equations to describe the motion. Our author chooses to write the generic equation this way. So again, A is amplitude. I guess I can add that to our list on the left. Amplitude meaning the maximum distance, whatever it is that's oscillating, the oscillator, the maximum distance it goes from its equilibrium position. In the case of the simulation with the mass on the spring, that amplitude, A, was how far I pulled the mass down originally. For the simulation that was a pendulum, A is how far I pulled the mass. Now, technically, with a simple pendulum, A could be just how far to the left I pulled it, or it could be the angle I pulled it. We can write the equation of motion for this pendulum in terms of an actual position in meters or an angle in radians specifically. So our author chooses to write the equation in terms of a cosine function. So A is our amplitude, omega is our angular frequency in radians per second, t is whatever moment in time we're trying to locate the position or describe the position. Phi naught is a phase constant or a phase shift. If you remember, a cosine function starts at a maximum value, and then the object oscillates, moving towards equilibrium. So this is an just cosine omega t function. The position would be a cosine omega t. The phase shift would be 0 because it is not shifted from equilibrium. If we were looking at the mass simulation where I pulled the mass down and we started the mass at its lowest point and let it oscillate, we would either need to say this is a negative cosine function, so the negative a cosine omega t would be perfectly valid, or if we wanted to write it in terms of a positive cosine function, we would need to add a phase shift. So the difference in radians between the maximum point and the bottom point is half an oscillation, so that would be pi radians. This is our phase shift. This phase shift accounts for the initial position. So x initial or y initial, whichever way we write the position. So it needs to be in this generic equation so that we remember to account for the initial position of the oscillator. We will do some examples with this in a later video. Ultimately, as we go back and we relate this to the circular motion and that circle with a peg, where it is at any given moment representing the shadow, this will represent the shift or the angle between that starting point and the original cosine function starting point versus our actual starting point. So we'll do some examples with that as we continue. And actually this video is probably long enough, so I will just make the next video talking about this generic motion. As we talk about position versus velocity or acceleration, we can basically apply what we've learned in our previous classes in terms of, well, if I have position, then I can get to velocity and acceleration and so forth. So as of right now, basic definitions of motion. Again, we're talking about ideal oscillations first. And we have some basic equations relating frequency and period, and this generic equation of motion, which we'll build on in the next video.